Right now, the universe is almost completely empty. Over 99% of it is just vacuum, cold dark, nothing stretching in every direction. If you gathered all the matter in every star, every planet, every speck of dust across the entire observable cosmos, it would fill barely a sliver of the space it occupies. And yet, look at the universe on the largest scales, and something astonishing appears. Matter is not scattered at random. It has organized itself into an architecture of breathtaking complexity. From tiny moons circling planets, to stars bounding clusters, to galaxies, to structures so vast they stretch across billions of light years. Tonight, we're going to walk through every level of that architecture. And by the end, you will understand why the universe looks the way it does. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with a question that seems simple, but opens up an enormous story. What exactly is a cosmic structure? When astronomers use that term, they mean something specific. A cosmic structure is any arrangement of matter in space that holds together or stands out as a recognizable pattern against the emptiness surrounding it. It could be something as intimate as a planet circling its star, or something as vast as a thread of galaxies stretching across 1 billion light years. Both count, but they are very different things, and understanding the difference is essential to understanding the universe. Here is the critical distinction most explanations skip over. There is a difference between an object, a system, and a large-scale pattern. A star is an object, a single thing, a ball of hydrogen and helium fusing elements in its core, held together by its own gravity. But a star orbited by planets is a system. The star and its planets are gravitationally bound to one another, moving together through space, connected by the invisible thread of gravity. And when you zoom out and see hundreds of billions of such systems arranged in a spiraling disk of light, you're looking at a galaxy, a vastly more complex structure that contains those smaller systems within it. Zoom out even further and you will see thousands of galaxies arranged along thin filaments, stretching across hundreds of millions of light years. That is a large-scale pattern, something not assembled by a single gravitational collapse, but instead shaped over billions of years by the interplay between gravity pulling matter together and the expansion of space, pushing it apart. Every level of structure in the universe connects to the next. Smaller structures nest inside larger ones. Planets orbit stars. Stars cluster into groups. Groups live inside galaxies. Galaxies gather into clusters, and those clusters are threaded along filaments that span the observable cosmos. It is one continuous hierarchy, built from the bottom up by the relentless pull of gravity, and we are going to walk through every level of it. It all begins with a cloud. Somewhere in the Milky Way, roughly 4.6 billion years ago, a vast cloud of gas and dust began to collapse under its own gravity. The cloud was enormous, probably spanning several light years across, made mostly of hydrogen and helium left over from the Big Bang, mixed with heavier elements that had been forged in the cores of earlier generations of stars, and scattered into space when those stars exploded. Something disturbed this cloud. Perhaps a shock wave from a nearby supernova, perhaps the gravitational tug of a passing star, perhaps just the random density fluctuations that exist in any large volume of gas. Whatever the cause, a region of the cloud became slightly denser than its surroundings, and gravity took over. Once a region of gas starts to collapse, the process tends to accelerate. The denser the region becomes, the stronger its gravitational pull, and the more material it draws in from the surrounding cloud. As the collapsing region shrank, it began to spin faster, the way an ice skater spins faster when pulling their arms in close. Conservation of angular momentum forced the material to flatten into a disk, a swirling pancake of gas and dust with a growing concentration of mass at its center. The center grew hotter and denser as more material piled on, until eventually the temperature and pressure became extreme enough to ignite nuclear fusion. Hydrogen atoms began slamming together and fusing into helium, releasing tremendous energy in the process. A star was born, our sun. But the disk of leftover material surrounding the young star did not just sit there. Within it, tiny grains of dust collided and stuck together. Over millions of years, those grains grew into pebbles, then rocks, then boulders, then bodies large enough that their own gravity started pulling in more material. This is the process astronomers call accretion. Small things sticking to other small things, gradually building larger and larger objects. Eventually, some of these growing bodies became massive enough to sweep up all the material in their orbital zone, clearing a path through the disk. These were the planets. Others remained smaller, becoming moons, asteroids, and comets. The entire arrangement, the star, and everything orbiting it is what we call a planetary system. And here is the remarkable thing. This process is not rare. It is not something that happened once around our sun and never again. It appears to be one of the most common outcomes of star formation in the entire universe. As of the mid-2020s, astronomers have confirmed the existence of more than 5,700 planets orbiting other stars, and the real number is almost certainly in the billions just within the Milky Way alone. The Kepler Space Telescope showed that virtually every star in the sky has at least one planet. Some have many more. There are systems with 7 or 8 planets packed tightly around a single star. There are systems with gas giants orbiting so close to their star that a full year passes in only a few days. There are systems with planets circling 2 stars at once, watching a double sunset every evening. Planetary systems are everywhere. They are the smallest and most common type of gravitationally bound cosmic structure, and they form naturally whenever a cloud of gas collapses to create a star. What makes this variety so significant is that every one of these systems form through the same basic physics. A disk of gas and dust around a young star, shaped by gravity and angular momentum. Yet, the outcomes are enormously diverse. The mass of the star, the amount of material in the disk, the timing of when giant planets form, and whether they migrate inward, random interactions with nearby stars, all of these variables produce planetary systems that look nothing like one another. Our own solar system, with small rocky worlds close to the sun and gas giants farther out, turns out to be just one possibility among many. Some systems are dominated by super-Earths, rocky worlds larger than our planet but smaller than Neptune, a category that does not exist in our solar system. The sheer range of outcomes tells us something fundamental. The same gravitational collapse can produce wildly different results depending on initial conditions. And this theme, similar physics producing diverse structures, will follow us all the way up the hierarchy. But stars do not always form alone. In fact, a surprisingly large fraction of all stars are born with at least one companion. When a collapsing cloud of gas fragments meaning it breaks apart into two or more dense cores rather than just one. The result is a multiple star system. Two stars orbiting a common center of gravity make a binary. Three stars make a triple. And some systems are even more complex than that. For Sun-like stars, roughly half exist in multiple star systems. For more massive stars, the fraction is even higher. Among the hottest and most luminous stars in the galaxy, the massive O and B type stars that burn blue-white and die young, something like 70 to 80% or more, have at least one stellar companion. Multiple star systems are not the exception. For many types of stars, they are the norm. The Alpha Centauri system, the closest star system to our Sun, is a perfect example. It contains 3 stars. Alpha Centauri A and Alpha Centauri B are a pair of Sun-like stars orbiting each other once every roughly 80 years. Far away from them, completing a much wider and slower orbit, is Proxima Centauri, a tiny red dwarf that happens to be the single nearest star to our solar system. All 3 are gravitationally bound, moving through space together as a unit, despite being separated by distances that would take our fastest spacecraft thousands of years to cross. Then there is Castor, a star visible to the naked eye in the constellation Gemini. What looks like a single point of light is actually a system of 6 stars. 3 pairs of binaries, all gravitationally bound to one another. Each pair consists of 2 stars orbiting each other closely, and the 3 pairs orbit their common center of mass in a complex gravitational dance that has been going on for hundreds of millions of years. Castor is a reminder that the universe is full of hidden complexity. What seems simple at first glance, a single point of light in the night sky, often turns out to be far more intricate when you look more closely. Multiple star systems form through the same basic mechanism as single stars. A cloud collapses, but instead of producing one dense core, it fragments into 2 or more. Each fragment continues collapsing independently, eventually igniting fusion and becoming a star. Because they formed from the same cloud, these stars are gravitationally linked from the very beginning. The result is a system, multiple objects bound by gravity and orbiting together, held in an embrace that can last billions of years. Now, let's go bigger. When a large region of gas gives birth to many stars at roughly the same time, the result is not just a few stars orbiting each other. It can be dozens, hundreds, or even thousands of stars, all born from the same parent cloud, all sharing roughly the same age and chemical composition, all moving through space in the same general direction. These larger groups come in several varieties, and the differences between them matter. The loosest type of stellar group is called a stellar association. These are collections of young stars that share a common origin but are not tightly bound by their mutual gravity. The most well-known type is the OB association, named after the massive O and B type stars that dominate them. These are the most luminous stars in the galaxy, blazing blue-white and burning through their fuel at a furious rate. They live only a few million years before dying in spectacular supernova explosions. Because they are so short-lived, finding a group of them together tells you something important. These stars must have formed recently, in astronomical terms, within the last few million years, from the same cloud of gas. But here is the key thing about stellar associations. They are falling apart. The stars within an association are not moving fast enough or packed tightly enough for their mutual gravity to hold them together permanently. They are slowly drifting apart, each star following its own path through the galaxy, gradually spreading out over tens of millions of years until the group is no longer recognizable as a group at all. Stellar associations are temporary structures. They exist for a cosmic blink and then dissolve, their stars scattering into the general population of the galaxy like guests leaving a party. There are also T-Tauri associations, groups of young low-mass stars still in the process of contracting and settling down before they begin their long, stable lives on the main sequence. These two are temporary gatherings, born from the same cloud but destined to drift apart within tens of millions of years. This is an important concept that applies throughout the hierarchy of cosmic structures. Not everything that exists is permanent. Some structures are gravitationally bound, meaning gravity is strong enough to hold them together indefinitely. Others are unbound, meaning they will eventually disperse. And still others sit on the boundary, loosely held together for a time, but destined to come apart. Knowing which category a structure falls into is fundamental to understanding it. A stellar association is unbound. It is a snapshot of a process, not a lasting arrangement. The stars were born together, but they will not stay together. Now compare that to an open cluster. Open clusters are also groups of stars born from the same molecular cloud, but they are denser and more tightly packed than associations. They contain anywhere from a few hundred to a few thousand stars, concentrated in a region that might span only 10 to 30 light years across. And crucially, open clusters are gravitationally bound, at least when they are young. The mutual gravity of all their stars is strong enough to hold the group together as a coherent structure moving through space. The Pleiades, sometimes called the Seven Sisters, is one of the most famous open clusters in the sky. It sits about 440 light years from Earth in the constellation Taurus, and on a clear dark night, you can see a handful of its brightest stars with the naked eye. A small tight knot of blue-white light. But those few visible stars are just the brightest members. The cluster actually contains well over 1,000 stars, most of them far too faint to see without a telescope. All of them formed from the same gas cloud roughly 100 million years ago. They are still traveling together through space, still held together by gravity, still recognizable as a family. The Hyades is another well-known open cluster, also in Taurus, much closer to us at about 150 light years away. The Hyades is older than the Pleiades, roughly 625 million years old, and it contains about 400 stars, spread across a somewhat larger volume of space. You can see part of it with the naked eye, a V-shaped pattern of stars near the bright orange star Aldebaran, though Aldebaran itself is not actually a member of the cluster. It just happens to lie along the same line of sight. The Hyades is slowly dissolving. Over hundreds of millions of years, gravitational interactions with other objects in the galaxy, encounters with giant molecular clouds, and the tidal pull of the Milky Way itself are gradually stripping stars away from the cluster. Eventually, the Hyades will cease to exist as a recognizable group. Its stars will be scattered individually throughout the galaxy, carrying no visible trace of their shared origin. This is the fate of most open clusters. They form, they hold together for a while, and then the galaxy slowly pulls them apart. Our own sun almost certainly formed in an open cluster roughly 4.6 billion years ago. The sun and perhaps a few thousand other stars condense from the same molecular cloud, born together as siblings. But that birth cluster dissolved long ago. The Sun's sibling stars have scattered across the galaxy over billions of years, and we have no easy way to identify them. They could be thousands of light years away by now, looking nothing like our Sun, carrying no visible sign of their shared origin. Some clusters survive a few 100 million years. A rare few persist for 1 billion years or more, but eventually almost all of them dissolve. The galaxy is not a gentle environment. It is full of gravitational disturbances, tidal forces, and encounters with massive clouds of gas, and open clusters are simply not massive enough to withstand them forever. There is a reason this matters for the larger story we are building. Every scale of structure in the universe has a characteristic lifetime. Stellar associations last tens of millions of years. Open clusters last hundreds of millions of years. The structures we will encounter later, galaxies, galaxy clusters, can survive for billions of years. Understanding these lifetimes helps you understand the difference between a fleeting arrangement and a lasting architectural element of the cosmos. But there is one type of star cluster that does endure. Globular clusters are among the oldest surviving structures in the entire universe, and they are nothing like open clusters. Picture a sphere. Not a loose scattering of stars like the Pleiades, but a dense, blazing sphere, packed with hundreds of thousands of stars, or even millions of them, all crammed into a region that might span only 100 to 300 light years across. The stars at the center of a globular cluster are so densely packed that if you lived on a planet there, your night sky would be ablaze. Thousands of stars would shine as brightly as Venus appears from Earth, and the combined glow would make true darkness impossible. You would never experience a fully dark night. Omega Centauri, the largest globular cluster associated with the Milky Way, contains roughly 10 million stars. That is more stars than most dwarf galaxies have. In fact, many astronomers believe Omega Centauri is not a true globular cluster at all, but the stripped core of a small galaxy that was swallowed by the Milky Way billions of years ago. Its stars are ancient, most of them more than 10 billion years old, born when the universe itself was only a few billion years into its existence. Looking at Omega Centauri is like looking at a fossil, a surviving fragment from one of the earliest epochs of cosmic structure formation. M13, sometimes called the Great Globular Cluster in Hercules, is another spectacular example. It sits about 22,000 light years from Earth and contains roughly 300,000 stars bound together in a tight gravitational embrace. When you look at M13 through a telescope, it appears as a dense ball of light, with individual stars blurring together toward the center into a continuous glow. The Milky Way has about 150 known globular clusters, and they orbit the galaxy in its halo, the roughly spherical region that surrounds the flattened disk of stars where our Sun lives. Some of these clusters follow elongated orbits that take them far above and below the galactic plane, swooping in close to the galactic center and then arcing back out to the distant halo. Their orbits tell us something profound about the history of the galaxy, because many of these clusters formed in the small protogalaxies that merged together billions of years ago to build the Milky Way we see today. Every globular cluster is a time capsule carrying chemical and dynamical fingerprints of the ancient environment where it was born. Globular clusters are gravitationally bound on a scale that open clusters cannot match. Their combined mass is enormous, and their stars are packed so tightly that the mutual gravity holds the entire system together for billions of years, resisting the tidal forces of the galaxy. They are survivors, relics from an era when the universe was still assembling its first large structures. Inside a globular cluster, stars pass close to one another, far more frequently than they do in the general galaxy. These close encounters gradually redistribute energy among the stars, a process called gravitational relaxation. Over billions of years, heavier stars sink toward the center while lighter stars drift outward. The cluster evolves dynamically even as it endures, its internal structure slowly shifting while the whole system remains gravitationally bound. Open clusters come and go, but globular clusters persist across cosmic time. Now, where do all of these stars and clusters come from? What builds them? This brings us to one of the most important structures in the entire hierarchy: molecular clouds. A molecular cloud is a vast, cold, dense region of gas and dust floating within a galaxy. The gas is mostly molecular hydrogen, two hydrogen atoms bonded together, mixed with trace amounts of helium and tiny quantities of heavier elements like carbon, oxygen, and silicon locked up in microscopic dust grains. These clouds are cold, typically only about 10 to 20 degrees above absolute zero, and they are dense by the standards of interstellar space, though they would still count as a far better vacuum than anything we can create in a laboratory on Earth. The key thing about molecular clouds is that they are the birthplaces of stars. Every star in the universe, including our Sun, formed inside one of these clouds. Giant molecular clouds are the largest of these stellar nurseries. They can span anywhere from 50 to over 300 light years across, and contain enough mass to form thousands or even tens of thousands of stars. The Orion Molecular Cloud Complex, which lies behind the visible Orion Nebula about 1,300 light years from Earth, it's one of the nearest and best studied examples. It stretches across hundreds of light years and contains enough gas to produce many thousands of new stars. The glowing Orion Nebula that you can see with the naked eye on a clear winter night is just the illuminated surface of this much larger dark cloud. The nebula glows because young hot stars embedded within it are blasting the surrounding hydrogen with intense ultraviolet radiation, causing the gas to fluoresce. But behind that glowing surface, hidden in the cold, dark interior, new stars are forming right now. Cores of gas are collapsing. Disks are flattening, and future planetary systems are beginning to take shape in the silence and darkness of the cloud's interior. The process of star formation inside a molecular cloud is the same gravitational collapse we have been talking about all along. A region of the cloud becomes slightly denser than its surroundings. Gravity pulls it together, it contracts, heats up, flattens into a disk, and eventually ignites a star at its center. But in a giant molecular cloud, this does not happen just once. It happens hundreds or thousands of times simultaneously. Different regions of the cloud collapse independently, each one forming its own star or group of stars. The result is a burst of star formation that can produce an entire population of stars, complete with open clusters, multiple star systems, and planetary systems in just a few million years. And star formation is not a gentle process. It is messy, violent, and self-regulating. When massive young stars ignite, they pour out enormous amounts of radiation and powerful stellar winds, blasting the surrounding gas with energy. This feedback can compress nearby gas, triggering new episodes of collapse and creating a chain reaction of star formation. But it can also blow gas away entirely, dispersing the cloud and shutting down further star birth in the region. The balance between these two effects, triggering new stars and destroying the material that feeds them, determines how efficiently a molecular cloud converts its gas into stars. Typically, only a few percent of a cloud's total mass actually ends up in stars before the rest is heated and blown away by the very stars the cloud produced. On an even larger scale, star-forming complexes are regions where multiple giant molecular clouds and their associated young stars, clusters, and glowing nebulae span hundreds or even thousands of light years. The Carina Nebula, about 7,500 light-years from Earth, is one of the most spectacular star-forming complexes in the Milky Way. It contains multiple star clusters, vast pillars of gas and dust sculpted by radiation, and some of the most massive and luminous stars known. These massive stars are actively reshaping their environment, carving cavities in the gas, while simultaneously compressing other regions into new rounds of star formation. Beyond our own galaxy, the Tarantula Nebula in the Large Magellanic Cloud, also known as 30 Doradus, is an even more extreme example. It is the most vigorous star-forming region in the entire local group of galaxies, producing stars at a rate far higher than anything in the Milky Way today. At its heart sits R136, a superstar cluster containing some of the most massive stars ever discovered. Individual stars more than 100 times the mass of our Sun. If the Tarantula Nebula were as close to us as the Orion Nebula, it would be bright enough to cast visible shadows on the ground at night. That is how intense its output of light and energy is. These molecular clouds and star-forming complexes are the factories of the cosmos. They produce the stars that populate open clusters, the stars that wander alone through the galaxy. And in the early universe, they produce the stars that built the globular clusters we still see orbiting galaxies today. Without molecular clouds and the star formation they drive, the universe would contain nothing but dark matter and thin, featureless gas. No stars, no planets, no light, no complexity of any kind. Everything that makes the universe visible and interesting traces back to the physics of gravitational collapse inside molecular clouds. Now, step back and notice what has happened. We start with the simplest gravitational system, a star with its planets, and we have climbed through multiple star systems, loose stellar associations, gravitationally bound open clusters, ancient globular clusters, and the vast molecular clouds that give birth to all of them. At every step, the same fundamental mechanism is at work. Gravity pulls matter together. Dense regions get denser. Smaller structures form first, and larger structures build from the assembly and accumulation of smaller ones. But here is what connects all of this to the much larger story we are about to tell. Every structure we have discussed so far exists inside a galaxy. Open clusters, globular clusters, molecular clouds, planetary systems, multiple star systems, all of them live within the body of a galaxy, orbiting its center, influenced by its gravitational field, shaped by its tides and its flows of gas. A galaxy is not merely a collection of stars scattered in space. It is a gravitational environment, a vast system that contains and shapes all the smaller structures within it. And galaxies themselves did not appear from nothing. They formed through the same process of gravitational collapse, but on a vastly larger scale, and driven primarily by something invisible. Something that makes up roughly 85% of all the matter in the universe, and yet has never been directly seen. Dark matter. Long before the first star ever ignited, dark matter was already collapsing into enormous structures called halos, pulling itself together under its own gravity in the darkness of the early universe. These halos became the scaffolding, the skeleton, the framework into which ordinary gas would eventually fall, cool, and form the first generations of stars and galaxies. Understanding dark matter halos is the key to understanding why galaxies exist at all and why they are distributed across the universe the way they are. That takes us to the next great level of the hierarchy, because once we understand how galaxies form and what holds them together, we can begin to see how they organize themselves into groups, clusters, and structures so vast that they make even an entire galaxy look small. The jump from star clusters to galaxies is enormous, but the jump from galaxies to the structures they form together is even more staggering. And it all follows from the same physics, the same gravity, the same process of matter flowing toward the densest regions of the universe, building complexity upon complexity in a hierarchy that stretches from the smallest moon orbiting its planet to the largest pattern the cosmos has ever produced. So far, everything we have explored, planetary systems, multiple star systems, stellar associations, open clusters, globular clusters, and the vast molecular clouds where stars are born, all of it exists inside a single kind of structure, a galaxy. And a galaxy is where the story of cosmic architecture truly begins to change in character. Because a galaxy is not just a bigger version of a star cluster. It is something fundamentally different. It is the first level of the hierarchy where the invisible substance we call dark matter becomes the dominant player, where the visible stars and gas we can see are merely a thin, luminous coating on an enormous invisible framework. Understanding galaxies means understanding that framework. And understanding that framework changes everything about how you see the universe. So what is a galaxy really? Most people picture a galaxy as a collection of stars, maybe with some gas and dust mixed in. That is not wrong, but it misses the most important part. A galaxy is a gravitationally bound system. It is a region of space where matter, both visible and invisible, has collapsed under its own gravity into a coherent structure that holds together over billions of years. A galaxy contains stars, yes, hundreds of millions of them in a small dwarf galaxy, hundreds of billions in a large spiral like the Milky Way, and up to 1 trillion or more in the largest ellipticals. But it also contains vast clouds of gas between the stars, lanes of dust that block and redden light, magnetic fields threading through the interstellar medium, and at the very center, a supermassive black hole whose mass can range from a few million to several billion times the mass of our sun. And surrounding all of this, extending far beyond the visible stars, is an enormous halo of dark matter that outweighs everything else combined. Every structure we discussed earlier lives within a galaxy. The open clusters, the globular clusters orbiting in the halo, the molecular clouds producing new generations of stars, the planetary systems, all of them exist inside this larger gravitational environment. A galaxy is the container that holds and shapes them. Its gravity influences their orbits. Its gas feeds star formation. Its tidal forces can rip apart smaller structures that wander too close to the center. A galaxy is not just a collection of objects. It is an ecosystem. Galaxies come in a variety of shapes. Astronomers have spent decades classifying them, and the full taxonomy can get quite detailed. But for our purposes, the key types are straightforward, and what matters most is not the differences between them, but what they all share. Spiral galaxies, like our own Milky Way, have a flat rotating disk of stars and gas with spiral arms winding outward from a central bulge. The disk is where most of the action happens. Molecular clouds in the disk produce new stars. Young, hot blue stars light up the spiral arms. Older, cooler stars populate the spaces between the arms and the central bulge. The Milky Way is a barred spiral, meaning it has a bar-shaped structure of stars running through the center, with the spiral arms extending from the ends of the bar. Spirals are active galaxies. They are still forming stars, still consuming gas, still evolving visibly. Elliptical galaxies are different. They are roughly spheroidal or egg-shaped collections of stars with very little gas or dust remaining. Star formation in most ellipticals has largely stopped. The stars within them are mostly old, giving these galaxies a reddish or yellowish color. Ellipticals range from small dwarf ellipticals containing a few million stars to enormous giant ellipticals containing 1 trillion or more. Many of the largest galaxies in the universe are giant ellipticals, grown fat over billions of years by swallowing smaller galaxies. Irregular galaxies fit into neither category. They have no clear spiral or elliptical shape, often because they have been gravitationally disrupted by interactions with nearby galaxies. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, are irregulars. The range of galaxy sizes is staggering. The smallest known galaxies, ultra-faint dwarfs, contain only a few thousand stars and span just a few hundred light years. The largest giant ellipticals can stretch across millions of light years and contain more than 1 trillion stars. The Milky Way, with its roughly 100,000 light-year diameter and its estimated 200 to 400 billion stars, falls somewhere in the upper range. It is genuinely large by cosmic standards, bigger than about 95% of all galaxies. But compared to the true giants, it is modest. But here is the crucial point. Regardless of shape, every galaxy is held together by gravity. Every galaxy sits inside a dark matter halo. Nearly every large galaxy has a supermassive black hole at or near its center, and every galaxy formed through the same fundamental process: the gravitational collapse of matter in the early universe, shaped by dark matter into the structures we observe today. The visible differences between spirals, ellipticals, and irregulars reflect differences in formation history, in how much gas was available, in whether the galaxy experienced major mergers. But the underlying physics is the same. The way a galaxy supports itself against gravitational collapse depends on its type. In a spiral, the disk is held up by ordered rotation. Stars, gas, and dust all orbit the galactic center in roughly the same direction. And this collective orbital motion prevents the disk from falling inward. In an elliptical galaxy, the mechanism is entirely different. There is no organized rotation. Instead, stars swarm in all directions on randomly oriented orbits. The combined random motion of billions of stars provides the outward pressure that balances gravity. These are fundamentally different solutions to the same problem, and understanding them is essential, because when astronomers first measured how fast stars were orbiting in spiral galaxies, the results shattered expectations. At the center of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass about 4 million times that of our Sun. It is surprisingly compact. All that mass is concentrated in a region smaller than the orbit of Mercury. Stars near the galactic center orbit this black hole at tremendous speeds. One star, known as S2, completes an orbit in only about 16 years, reaching speeds of about 2.5% of the speed of light at its closest approach. Despite its enormous mass, Sagittarius A star is relatively quiet right now. It is not actively consuming large amounts of material, but in other galaxies, supermassive black holes can be spectacularly active, devouring gas and producing jets of energy that extend for hundreds of thousands of light years. The black hole at the center of M87, for example, has a mass of roughly 6.5 billion times that of our Sun, and was the first black hole ever directly imaged in 2019. Supermassive black holes are a universal feature of galaxies. Nearly every galaxy we have examined closely enough has one at its heart. They are not just incidental features. They appear to play a role in regulating how galaxies grow and evolve. Now, here is where the story takes a dramatic turn. If you add up all the visible matter in a galaxy, all the stars, all the gas, all the dust, you get a certain total mass. And then if you look at how the galaxy is actually behaving, how fast its stars are orbiting, how strongly it bends the light of more distant objects behind it, you find that the visible matter is not nearly enough to explain what you see. Something else must be there. Something massive. Something invisible. Something that exerts gravity but produces no light. This is dark matter. And its discovery changed everything we thought we knew about what galaxies are. The first hint came in 1933 from a Swiss astronomer named Fritz Zwicky. Zwicky was studying the Coma cluster, a large collection of galaxies about 330 million light-years from Earth. He measured how fast the individual galaxies within the cluster were moving, and found something disturbing. They were moving far too fast. Based on the total amount of visible matter in the cluster, the stars and gas he could see, the galaxies should have been moving much more slowly. At the speeds he measured, the cluster should have flown apart long ago. The galaxies were moving so fast that the gravity of all the visible matter combined was not nearly strong enough to hold the cluster together. Zwicky concluded that there had to be a huge amount of unseen mass in the cluster, something he called dark matter. His estimates suggested the cluster contained roughly 400 times more mass than was visible. The actual ratio turned out to be somewhat smaller, but the basic conclusion was correct. Most of the mass was invisible. For decades, Zwicky's result was largely ignored. It seemed too strange, too radical. But in the 1970s, an American astronomer named Vera Rubin provided evidence that was impossible to dismiss. Rubin was studying the rotation of spiral galaxies. In a spiral galaxy, stars orbit the galactic center much like planets orbit a star. You would expect stars far from the center to orbit more slowly than stars near the center, just as Neptune orbits the Sun far more slowly than Mercury does. This is because in a simple system where most of the mass is concentrated at the center, the gravitational pull weakens with distance, and objects farther out need less speed to maintain their orbits. But that is not what Rubin found. Working alongside astronomer Kent Ford, who had built a remarkably sensitive spectrograph capable of measuring the speeds of stars in distant galaxies, Rubin measured the orbital speeds of stars at different distances from the centers of spiral galaxies. What she discovered stunned the astronomical community. Stars in the outer regions of these galaxies were orbiting just as fast as stars much closer to the center. In some cases, they were orbiting even faster. The rotation curves were flat. They did not decline with distance the way they should have if visible matter were all there was. This meant there had to be a tremendous amount of additional mass in the outer regions of these galaxies, far beyond where most of the stars were located. Something invisible was out there, exerting gravitational pull, keeping those outer stars moving at unexpectedly high speeds. Rubin's work was careful, methodical, and ultimately undeniable. She measured rotation curves for galaxy after galaxy, and the result was always the same: flat rotation curves. Every spiral galaxy she studied showed the same signature of invisible mass in its outskirts. The evidence was overwhelming. Galaxies were embedded in vast halos of dark matter that extended far beyond the visible stars, and these halos contained far more mass than the visible galaxy itself. Think about what this means. When you look at a galaxy through a telescope, when you see that beautiful spiral or that glowing elliptical ball of stars, you are seeing only a small fraction of the total structure. The visible galaxy, the part made of stars and gas and dust, is like the tip of an iceberg. Beneath the surface, invisible but massive, is an enormous dark matter halo that dwarfs the visible component. In a typical galaxy, dark matter makes up roughly 80 to 90% of the total mass. The stars, the gas, the dust, everything you can actually see accounts for only about 10 to 20%. We are looking at the universe and seeing only a fraction of what is actually there. The Milky Way is no exception. Our galaxy's visible disk of stars is about 100,000 light years across, but its dark matter halo extends much further, probably out to 300,000 light years or more, possibly as far as 600,000 light years. That means the dark matter halo is several times wider than the visible galaxy in every direction. If you could somehow make dark matter glow, the Milky Way would look entirely different. The beautiful spiral disk that we know would be a small bright patch at the center of an enormous, roughly spherical cloud of softly glowing dark matter. The halo is not uniform. It is densest at the center and becomes more diffuse toward the edges, fading gradually into the intergalactic medium. This invisible halo contains roughly 10 times as much mass as all the visible stars and gas combined. When astronomers talk about the total mass of the Milky Way, they usually quote a figure of about 1 to 1.5 trillion times the mass of our Sun. Most of that mass is dark matter. The hundreds of billions of visible stars contribute only a small fraction. So, what is dark matter? That is one of the greatest unsolved questions in physics. We know what it does. It exerts gravity, it clumps together into halos, it provides the scaffolding on which visible matter collects. But we do not know what it is made of. It is not ordinary matter, not protons and neutrons and electrons. It does not emit light. It does not absorb light. It does not interact with the electromagnetism at all, which is why we cannot see it. It passes through ordinary matter almost without interaction, like a ghost moving through walls. The leading candidates are exotic subatomic particles that have not yet been detected in laboratories. Weakly interacting massive particles, often called WIMPs, have been the favored hypothesis for decades. Enormous detectors have been built deep underground, shielded from cosmic rays, waiting patiently for a dark matter particle to collide with an ordinary atom. Particle accelerators like the Large Hadron Collider have searched for signs of dark matter production in high-energy collisions. So far, nothing. Other candidates include ultralight particles called axions, sterile neutrinos, and various other theoretical possibilities. Despite decades of effort and some of the most sensitive experiments ever constructed, no dark matter particle has been conclusively identified. We know dark matter is there. We can measure its effects with extraordinary precision, but its true nature remains one of the deepest mysteries in all of physics. But even though we do not know what dark matter is made of, we have very strong evidence that it exists as a real substance, rather than being an illusion caused by our misunderstanding of gravity. One of the most powerful pieces of evidence comes from the bullet cluster, a pair of galaxy clusters that collided about 150 million years ago. When the two clusters slammed into each other, the hot gas in each cluster, which makes up most of the ordinary matter, was slowed down by the collision. It piled up in the middle, like two clouds of steam colliding. But the dark matter, which does not interact with itself or with ordinary matter except through gravity, passed right through. It kept going, separating from the gas. Astronomers could map where the mass was by using gravitational lensing, the bending of light from more distant galaxies behind the cluster. When a massive structure sits between us and more distant galaxies, its gravity warps the fabric of space, bending the paths of light passing through. The distant galaxies appear smeared into thin luminous arcs curving around the cluster, their shapes stretched and distorted by the warped geometry of space. These eerie, glowing arcs are among the most visually dramatic phenomena in all of astronomy. And by measuring how strongly the light is bent, astronomers can calculate exactly how much total mass is present and where it sits, whether or not that mass produces any light. What they found was striking. The mass was not where the gas was. The mass was where the dark matter had ended up, on either side of the collision. The visible matter and the invisible matter had been physically separated by the collision, and the gravity followed the dark matter, not the gas. This is extremely difficult to explain if dark matter does not exist. It is exactly what you would expect if dark matter is a real substance that interacts gravitationally but barely interacts in any other way. Now, here is where the story of dark matter connects to the story of how galaxies formed. And this is perhaps the most important idea in all of modern cosmology. Dark matter did not just accumulate around galaxies after they formed. Dark matter formed the structures first. The galaxies came later. In the very early universe, just a few 100,000 years after the Big Bang, the cosmos was a nearly uniform soup of matter and radiation. But it was not perfectly uniform. Tiny density fluctuations existed, regions that were slightly denser or slightly less dense than average. These fluctuations were incredibly small, perhaps 1 part in 100,000. We can actually see them. They are imprinted in the cosmic microwave background, the faint glow of radiation left over from the early universe that fills all of space. Maps of this radiation, produced by spacecraft like the Planck satellite, show tiny temperature variations that correspond to those primordial density differences. If you have ever seen one of these maps, it looks like a mottled oval, painted in faint patches of blue and red. The blue spots mark regions that were fractionally cooler and denser. The red spots mark regions that were slightly warmer and less dense. The differences are almost impossibly small, but those faint patches are the seeds of everything. Every galaxy, every cluster, every filament of the cosmic web grew from one of those barely visible variations. Dark matter responded to these fluctuations first. Because dark matter interacts only through gravity, it was free to begin collapsing while ordinary matter was still trapped in a hot plasma, unable to clump because radiation pressure kept pushing it apart. dark matter began falling into the slightly denser regions, accumulating there, forming the first gravitational wells. These early dark matter concentrations grew over time, pulling in more dark matter from their surroundings. Small clumps merged with other small clumps, forming larger structures. This hierarchical assembly, small things merging to make bigger things, is the fundamental process by which structure grew in the universe. It is the same bottom-up building process we saw with star clusters and stellar associations, but now operating on a vastly larger scale and driven entirely by dark matter. Eventually, about 380,000 years after the Big Bang, a critical transition occurred. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, an event cosmologists call recombination. With atoms finally formed, radiation decoupled from matter and streamed freely through space, becoming what we now observe as the cosmic microwave background. More importantly for our story, ordinary matter was finally free to respond to gravity without radiation pressure holding it back. Gas began streaming into the gravitational wells that dark matter had already dug, falling inward, heating up from compression, then cooling and condensing into dense clumps. Within those clumps, the first stars ignited. And around those stars, within those dark matter halos, the first galaxies were born. This epoch, roughly the first billion years after the Big Bang, is what astronomers call cosmic dawn. It was a period of furious activity. The first stars were enormous, often hundreds of times the mass of our sun, burning through their fuel in a few million years and dying in violent explosions that enriched the surrounding gas with heavy elements for the first time. The light from these earlier stars gradually ionized the neutral hydrogen that filled the universe, ending the cosmic dark ages and making the universe transparent. These first galaxies were small. They were not grand spirals like the Milky Way. They were tiny, irregular collections of a few million stars, each one sitting at the center of its own dark matter halo. But the process of hierarchical assembly continued. Small galaxies merged with other small galaxies. Their dark matter halos combined. Their stars mixed together. Their gas pools merged and triggered new waves of star formation. Over billions of years, these mergers built progressively larger galaxies. The Milky Way itself is the product of many such mergers. Studies of the chemical compositions and motions of stars in our galaxy have identified the remnants of several ancient dwarf galaxies that were absorbed by the Milky Way billions of years ago. One of the most significant, sometimes called the Gaia sausage or Gaia Enceladus, was a dwarf galaxy that collided with the Milky Way roughly 8 to 10 billion years ago. Its stars are still identifiable today by their distinct chemistry and their elongated orbits. They form a population of stars scattered through the inner halo, a fossil record of a violent event that helped shape our galaxy into the structure it is today. Each merger contributed stars, gas, and dark matter to the growing whole. This process of growth through mergers continues today. The Sagittarius dwarf elliptical galaxy is currently being torn apart and absorbed by the Milky Way. The Magellanic Clouds will eventually meet the same fate. And in roughly 4.5 billion years, the Milky Way and the Andromeda Galaxy will merge into a single larger galaxy, combining their dark matter halos, their stars, and their gas into a new structure. Galaxy formation is not a single event. It is a process that has been going on for over 13 billion years and continues today. Galaxies are not fixed. finished objects, and they are dynamic, evolving systems that grow by consuming gas, merging with other galaxies, and forming new generations of stars. The dark matter halo provides the gravitational foundation for all of this activity. Without dark matter, the gas would never have had anywhere to collapse into. Without dark matter halos, there would be no galaxies. This brings us to a crucial realization about the hierarchy of cosmic structures. At the scale of star clusters, visible matter is the star of the show. The gravity of the stars themselves is what holds an open cluster or globular cluster together. Dark matter plays no significant role at those scales. But at the scale of galaxies, the balance shifts dramatically. Dark matter takes over. The visible galaxy, with all its stars and gas and dust, is a relatively minor component of the total system. The dark matter halo is the primary structure. The visible galaxy is the secondary structure that formed within it. And this shift only becomes more pronounced as we continue to larger scales. When galaxies gather into groups and clusters, dark matter becomes even more dominant. The hot gas between galaxies in a cluster contains more mass than all the galaxy's stars put together, and the dark matter outweighs even the hot gas by a factor of 5 or 6. At the scale of the cosmic web itself, the vast filaments and sheet that span the observable universe, the underlying framework is made almost entirely of dark matter. Visible matter traces this framework, collecting in the densest regions, forming galaxies and clusters where the dark matter scaffolding is thickest. But the scaffolding itself, the architecture that gives the universe its structure, is invisible. Think of it this way. If you could somehow remove all the dark matter from the universe and leave only the visible matter, the entire cosmic architecture would collapse. Galaxies would fly apart, clusters would disperse, the web of filaments would dissolve. The beautiful, large-scale structure of the universe would simply cease to exist. Dark matter is not a minor addendum to the story of cosmic structure. It is the foundation on which everything else is built. Now, recall what we said about smaller structures being embedded within galaxies. Every open cluster in the Milky Way orbits within the galaxy's gravitational field, which is dominated by dark matter. Every globular cluster arcing through the halo follows an orbit shaped by the dark matter distribution. Every molecular cloud forming new stars sits within a gravitational environment created overwhelmingly by invisible matter. The planetary systems within those clouds, the stars within those clusters, even our own solar system orbiting 26,000 light years from the galactic center, all of them are embedded in and shaped by a dark matter structure they cannot see, touch, or detect directly. We live our entire lives inside a dark matter halo, surrounded by it at all times, and we have absolutely no way of sensing it, except through the gravity it exerts on the things we can see. This is a profound and somewhat unsettling realization. Most of the universe is invisible. Most of the mass in your own galaxy is something that passes through your body every second without interacting with a single atom of your being. The ground you stand on, the air you breathe, the stars you see at night, these are the exception, not the rule. They are the small visible fraction of a cosmos dominated by darkness, but it is that small visible fraction that makes the universe interesting. Because it is in the visible matter, in the gas and dust and stars, that complexity arises. Dark matter provides the gravitational scaffolding, but it does not form molecules. It does not undergo chemistry. It does not build planets or produce life. All the richness and complexity of the universe, from molecules to cells to ecosystems to civilizations, exist in the thin, luminous layer of ordinary matter that coats the dark matter framework. We are made of the minority component, but we are the part that learned to ask questions about the whole. Galaxies, then, are not what they appear to be. They appear to be collections of stars, glowing disks and spheres visible through our telescopes. But in reality, each one is a thin shell of light surrounding an enormous invisible mass. The dark matter halo is the primary structure, and the visible galaxy is the decoration. Every galaxy in the universe, from the smallest dwarf to the largest giant elliptical, follows this pattern. Understanding this is essential to understanding everything that comes next. Because as we continue climbing the hierarchy of cosmic structures, from galaxies to groups, from groups to clusters, from clusters to the vast filaments and voids of the cosmic web, dark matter will remain the dominant ingredient at every scale. The visible universe is a tracer, a set of luminous signposts marking the peaks and ridges of an invisible landscape. And it is that invisible landscape, carved by gravity over billions of years from the tiny density fluctuations left behind by the Big Bang, that gives the cosmos its shape. So now we are ready to take the next step. We understand that galaxies are not isolated objects floating independently through space. They formed within a connected web of dark matter, and they remain connected to that web today. Galaxies have neighbors. They feel each other's gravity. They orbit around shared centers of mass. They fall toward concentrations of dark matter that draw them in. And when enough galaxies collect in one region of space, bound together by the gravity of a shared dark matter halo far more massive than any single galaxy, we get something new. Something larger. A galaxy group or a galaxy cluster. And these structures have properties that are as surprising as anything we have encountered so far. Galaxies do not exist in isolation. They have neighbors. And just as gravity pulls stars into clusters within a galaxy, gravity pulls galaxies themselves into larger structures. The simplest and most common of these is the galaxy group. A galaxy group is exactly what it sounds like. It is a small collection of galaxies held together by their shared gravitational pull, all embedded within a common dark matter halo. A typical galaxy group contains anywhere from a few to a few dozen galaxies, spanning a few million light years across. Groups are the most common environment for galaxies in the universe. Most galaxies, including our own Milky Way, live in groups rather than in larger, denser structures. If you picked a random galaxy from the cosmos, the odds are good that it would be a member of a small galaxy group orbiting quietly through space with a handful of companions. Galaxy groups form the same way everything else in the hierarchy forms. Dark matter collapses first, creating a gravitational well large enough to encompass several galaxy-sized halos. Individual galaxies that formed within this larger region, or that wandered in from nearby, become trapped by the combined gravitational pull. Over billions of years, the group settles into a loosely bound system with its galaxies orbiting the common center of mass. Some groups are compact, with galaxies packed relatively close together and interacting frequently. Others are loose, with galaxies spread over millions of light years, barely aware of each other except through the gentle tug of their shared gravity. Our own group is called the local group. It contains more than 50 known galaxies spread across roughly 10 million light years. But this is not a collection of equals. The local group is dominated by two large spirals, the Milky Way and Andromeda, also known as M31. These are the gravitational anchors, the two heavyweights around which everything else orbits. Between them, they account for the overwhelming majority of the group's visible mass and most of its dark matter as well. Triangulum, also known as M33, is a smaller spiral with roughly 40 billion stars. It may be a satellite of Andromeda rather than an independent member. And then there are the dwarfs. Dozens of them. Small, faint galaxies containing anywhere from a few million to a few billion stars each. The Large and Small Magellanic Clouds are among the most prominent, visible from the southern hemisphere as fuzzy patches of light. Most of the other dwarfs are so faint they were only discovered in recent decades with modern telescopes and survey techniques. The galaxies within the local group are gravitationally bound to one another. They orbit a common center of mass located somewhere between the Milky Way and Andromeda. They interact with each other. The Milky Way is slowly consuming the Sagittarius dwarf galaxy right now, pulling it apart with tidal forces. The Magellanic Clouds are connected to the Milky Way by a long stream of hydrogen gas called the Magellanic Stream, pulled out of the clouds by the Milky Way's gravity as they orbit. And of course, the Milky Way and Andromeda are falling toward each other, drawn by mutual gravity on a collision course that will result in a merger roughly 4.5 billion years from now. This is what a galaxy group looks like up close. A few large galaxies surrounded by many small ones, all orbiting within a shared dark matter halo, interacting gravitationally, occasionally merging, slowly evolving as a connected system. The dark matter halo of the local group extends well beyond the visible galaxies. Its total mass, including dark matter, is estimated as several trillion times the mass of our Sun. The visible galaxies account for only a small fraction of that total. Just as with individual galaxies, most of the mass in a galaxy group is dark matter. Galaxy groups are common throughout the universe. They are the basic building blocks of cosmic large-scale structure. Everywhere astronomers look, they find galaxies gathered into small groups, bound by gravity, embedded in shared halos. But some regions of the universe are much denser than others, where many groups have fallen together into a particularly deep gravitational well. Something much larger and more dramatic forms. A galaxy cluster. Galaxy clusters are among the most massive gravitationally bound structures in the entire universe. They contain not dozens but hundreds or even thousands of galaxies, all held together within an enormous dark matter halo that can span 10 million light years or more across. If a galaxy group is a small town, a galaxy cluster is a major city. Galaxy clusters did not spring into existence fully formed. They assembled over billions of years through continuous accretion. It began with a particularly massive dark matter halo at a node of the emerging cosmic web. That halo attracted nearby galaxies, drawing them in one by one and group by group along the connecting filaments. Small galaxy groups fell in along these threads, their combined mass adding to the cluster's gravitational pull, which attracted still more material from farther away. Over billions of years, the cluster grew larger and more massive, its gravitational well deepening, its reach extending further. Many of the largest galaxy clusters today are still actively accreting material, still growing. A galaxy cluster is not a finished object. It is an ongoing construction project spanning most of cosmic history. The Virgo cluster, located about 54 million light-years from Earth, is the nearest large galaxy cluster to the local group. It contains somewhere between 1,300 and 2,000 galaxies, ranging from giant ellipticals to small dwarfs. The cluster spans roughly 15 million light-years across, a volume of space so large that light takes 15 million years to cross it. At its heart sits M87, a giant elliptical galaxy containing roughly 1 trillion stars and one of the most massive black holes ever measured, whose gravity dominates the dynamics of the entire cluster. The Virgo cluster is the gravitational center of our region of the universe. Its mass is so great that the local group and everything around it is being pulled slowly toward it. The Coma cluster, about 330 million light-years away, is another prominent example, and a historically important one, because this is the cluster where Zwicky first noticed the dark matter discrepancy. The Coma cluster contains over 1,000 galaxies, and is one of the richest and most densely packed clusters known. Its total mass is estimated at several 100 trillion times the mass of our Sun. But here is the truly surprising thing about galaxy clusters, and it is one of the most remarkable facts in all of astronomy. The galaxies themselves, the bright objects you can see through a telescope, are actually a minor component of the cluster's total mass. The galaxies contribute only a few percent, typically around 2 to 5%, of the cluster's total mass. The majority of the cluster is something else entirely. Most of the ordinary matter in a galaxy cluster is not in the galaxies at all. It is in the space between them. The space between galaxies in a cluster is filled with an incredibly hot, thin gas called the intracluster medium. This gas has been heated to temperatures of tens of millions of degrees, sometimes exceeding 100 million degrees, which is far hotter than the surface of any star. At these extreme temperatures, the gas is fully ionized. Electrons have been stripped from their atoms, near creating a plasma that glows brightly in X-rays. You cannot see the intracluster medium with an optical telescope. It is invisible in visible light. But point an X-ray telescope at a galaxy cluster, and the gas lights up, filling the entire space between the galaxies with a diffuse glow. Where did this gas come from? Some of it was there from the beginning. Primordial gas that fell into the cluster's gravitational well during its formation, heated by compression as it fell. Some of it was stripped from individual galaxies as they plunged through the cluster. When a galaxy falls into a dense cluster environment, the pressure of the surrounding intracluster medium can strip gas right out of the galaxy, a process astronomers call ram pressure stripping. Imagine driving a car through a rainstorm at high speed. The rain hits the car and pushes water off the surface. Ram pressure stripping works in a similar way. A galaxy plowing through the dense hot gas of a cluster at hundreds or even thousands of kilometers per second experiences enormous pressure on its leading edge. That pressure pushes the galaxy's own gas out from behind, stripping it away like wind tearing leaves from a tree. Astronomers have actually observed this happening. In some clusters, galaxies have been photographed with long tails of gas streaming behind them, visibly being stripped by the intracluster medium as they fall inward. These are sometimes called jellyfish galaxies because of their trailing tentacles of gas. Over time, galaxies and clusters tend to lose much of their gas to this process, which is one reason why cluster galaxies tend to be gas-poor ellipticals rather than gas-rich spirals. The cluster environment transforms the galaxies within it, stripping away the raw material for star formation and slowly shutting down the production of new stars. A spiral galaxy that falls into a cluster may eventually become a red, dead elliptical. starved of the gas it needs to form new generations of stars. The cluster does not just contain galaxies, it changes them. It transforms spirals into ellipticals, turns vibrant star-forming systems into quiescent relics. This is why the centers of galaxy clusters are dominated by elliptical galaxies. They were not all born that way. Many were reshaped by the cluster environment itself. The total mass of hot gas in a typical galaxy cluster is enormous. It outweighs all the stars in all the galaxies in the cluster combined, usually by a factor of 3 to 5. In other words, if you could somehow weigh everything in a galaxy cluster, the hot invisible gas between the galaxies would weigh several times more than the galaxies themselves. The galaxies, those bright, beautiful objects that seem like the important things, are actually the lighter component. The heavier component is an ocean of superheated plasma that you can only see with X-ray eyes. And even the hot gas is not the main ingredient. Dark matter is. The mass budget of a typical galaxy cluster breaks down roughly like this. About 80 to 85% of the total mass is dark matter. About 12 to 15% is the hot intracluster gas, and only about 2 to 5% is in the form of stars, galaxies, dust, and everything else we normally think of as matter. Dark matter dominates. The hot gas is second. And the galaxies, the things we actually see when we look at a cluster, come in a distant third. This means that when you look at a photograph of a galaxy cluster, a stunning image showing hundreds of galaxies scattered across the sky, you are seeing only a few % of what is actually there. The overwhelming majority of the cluster is invisible. It is dark matter and hot gas, a massive gravitational well filled with superheated plasma, and the galaxies are almost an afterthought, tiny luminous islands floating in an invisible sea. If a galaxy cluster were an ocean, the dark matter would be the water, the hot gas would be the dissolved salts and minerals, and the galaxies would be a few grains of sand scattered across the ocean floor. That is how minor the visible component really is. So, what distinguishes a galaxy group from a galaxy cluster? There is no sharp dividing line. The distinction is more of a continuum than a clean boundary. Generally, astronomers classify a structure as a group if it contains fewer than about 50 galaxies, and as a cluster if it contains more. But the real difference is mass. Clusters are far more massive than groups. Their dark matter halos are deeper. They are hot enough and dense enough to contain that enormous reservoir of superheated gas, which groups generally are not. Groups tend to be cooler, less massive, and less extreme. The local group, for example, does not have a significant intracluster medium. It is not hot enough or dense enough. But the coma cluster, with its enormous mass, has an intracluster medium so hot and bright that it was one of the first cosmic X-ray sources ever detected. The transition from group to cluster is gradual, but the result is a qualitative change in the character of the structure. Clusters are different not just in size, but in kind. Now let's go bigger still. Because galaxy groups and clusters are not the end of the hierarchy. They themselves are organized into even larger structures called superclusters. And this is where the story takes an important turn, because superclusters are fundamentally different from everything we have discussed so far. A supercluster is a vast region of space that contains multiple galaxy groups and clusters, all connected by shared gravitational flows. Superclusters span hundreds of millions of light years. They are among the largest coherent structures astronomers have identified in the universe. But here is the critical distinction that most popular explanations get wrong. Superclusters are generally not fully gravitationally bound. Let me explain why that matters. Every structure we have discussed up to this point, planetary systems, star clusters, galaxies, galaxy groups, galaxy clusters, is gravitationally bound. The gravity within each of these structures is strong enough to hold them together permanently against any outside force. The objects within them may orbit, collide, and merge, but they do not escape. The structure as a whole persists. If you removed everything else in the universe and left only the local group, its galaxies would continue to orbit each other forever. If you left only the coma cluster, its galaxies and gas would remain bound in that deep gravitational well indefinitely. These are self-contained gravitational systems. They are permanent features of the universe, structures that will outlast nearly everything around them. Superclusters are different. At the scale of superclusters, we are entering the regime where the expansion of the universe begins to compete seriously with gravity. The universe is expanding. Space itself is stretching, carrying galaxies apart. For structures that are small and dense enough, gravity overwhelms this expansion. The local group is not expanding. The Milky Way is not getting farther from Andromeda. Gravity has won that battle, but at the scale of hundreds of millions of light years, the cumulative effect of cosmic expansion becomes significant. Parts of a supercluster that are not dense enough, that do not have enough gravitational pull to overcome the expansion, are slowly being pulled apart. They are connected now, they share common flows, they appear to be part of the same structure. But they will not remain together forever. Over billions of years, cosmic expansion will stretch the more tenuous regions of the supercluster apart, separating structures that are currently neighbors. This is where the concept of laniakea becomes important. In 2014, a team of astronomers led by Brent Tully published a landmark paper that redefined our understanding of the supercluster that contains the Milky Way. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is enormous. It spans roughly 520 million light years and contains approximately 100,000 galaxies. The Milky Way, our local group, the Virgo cluster, and many other structures are all part of Laniakea. What Tully's team showed was that Laniakea could be defined by the flow of galaxies. Within Laniakea, galaxies are flowing toward a common gravitational center, a region of space where the concentration of mass is great enough to pull everything in the surrounding volume inward. This region, long known as the Great Attractor, lies in the direction of the constellations Centaurus and Norma, roughly 150 to 250 million light years from us. The Great Attractor is not a single object. It is a concentration of galaxy clusters and superclusters, including the Norma cluster, whose combined gravity creates a basin of attraction. Every galaxy within Laniakea is falling toward this basin, including our own. But Laniakea is not gravitationally bound as a whole. Its outer regions are being influenced by the Hubble flow, the general expansion of space. Some galaxies currently within the Laniakea basin will eventually be pulled away by the expansion of the universe, carried off toward other attractors. The boundary of Laniakea is not a wall, it is a watershed, a dividing line between regions flowing toward the Great Attractor and regions flowing toward other gravitational centers. Galaxies near this boundary are on the knife's edge, pulled in competing directions by different attractors and by the expansion of space itself. And Laniakea is not the only supercluster. Beyond it, in the direction of the constellation Centaurus, lies the Shapley supercluster, an even more massive concentration of galaxy clusters roughly 650 million light-years away. The Shapley supercluster contains thousands of galaxies with a total mass estimated at roughly 10 quadrillion times the mass of our Sun. Its gravitational pull is so strong that it appears to be tugging on Laniakea itself, adding to the flow toward the great attractor and pulling structures in our part of the universe even faster in that direction. The interplay between Laniakea and the Shapley supercluster illustrates a broader point. At these scales, the universe is a landscape of competing gravitational basins, each trying to pull matter toward its center, with cosmic expansion working to separate them all. This is a profound shift in how we think about cosmic structures. Below the supercluster scale, structures are permanent. Galaxies, groups, and clusters will persist for billions of years, held together by gravity. But at the supercluster scale, structures are transient. They exist as coherent flows in the present epoch, but they are not guaranteed to hold together in the future. The competition between gravity and expansion means that the largest bound structures in the universe are probably galaxy clusters, not superclusters. Anything larger than a cluster is likely to be partially or completely dismantled by cosmic expansion over the coming billions of years. And this competition is getting worse. The expansion of the universe is not constant. It is accelerating. In 1998, two independent teams of astronomers made a shocking discovery. They found that the expansion of the universe, which everyone expected to be slowing down due to the gravitational pull of all the matter in the cosmos, was actually speeding up. Something was pushing space apart faster and faster. This mysterious force, called dark energy, makes up roughly 68% of the total energy content of the universe. We do not know what it is. We do not understand why it exists. But its effect is clear. It is driving the expansion of space to accelerate, which means the battle between gravity and expansion is tilting further and further in favor of expansion. In the distant future, dark energy will win completely at large scales. Structures that are not already gravitationally bound will be pulled apart. Superclusters will dissolve. The flows that currently define Laniakea will dissipate. Galaxy groups and clusters will persist, held together by their deep gravitational wells, and within them, individual galaxies will continue to orbit and occasionally merge. But the connections between clusters will break. Each cluster will become an island, isolated in an ever-expanding ocean of empty space, with nothing visible beyond its own gravitational boundary. Billions of years from now, observers in what remains of the Milky Way, by then merged with Andromeda into a large elliptical, will look out and see nothing beyond their own cluster. Every other galaxy cluster will have receded beyond the observable horizon, carried away by the expansion of space faster than light can bridge the gap. They will be alone. Not because other galaxies stopped existing, but because the universe expanded so much that no signal from those galaxies can ever reach them. The night sky beyond their own cluster will be permanently black. This future isolation is not speculation. It is a direct consequence of the accelerating expansion that we are already measuring. The universe is slowly disconnecting itself. severing the gravitational links between structures that are too far apart and too weakly bound to resist the stretching of space. Now, there is an important subtlety that we should address before moving on. The categories we have been using, galaxy group, galaxy cluster, supercluster, are not mutually exclusive boxes that a galaxy gets sorted into. They are overlapping descriptions of a continuous distribution of matter. A single galaxy can belong to several of these categories simultaneously. Take the Milky Way as an example. The Milky Way is a galaxy. It is also a member of the local group, a galaxy group. The local group is part of the Virgo supercluster, which is itself a component of Laniakea. At the same time, the local group sits along a filament of the cosmic web, connected by dark matter and thin strands of gas to other groups and clusters in our vicinity. And the Milky Way exists in a region that is also described as being on the outskirts of the Virgo cluster's sphere of influence, slowly being pulled toward it. None of these descriptions contradicts the others. They are all true at the same time. They simply describe different levels of the hierarchy, different scales at which the distribution of matter can be characterized. This is worth emphasizing because it can be confusing. When you hear that the Milky Way is part of Laniakea, that does not mean it stopped being part of the local group. When you hear that the local group is falling toward the Virgo cluster, that does not mean we are inside the Virgo cluster. These are nested and overlapping descriptions, not competing ones. The universe's matter distribution is continuous. The labels we apply are human conveniences that help us talk about different scales of organization, but the actual distribution of matter does not care about our labels. It flows and clusters and filaments at all scales simultaneously. There is a related issue that deserves attention. You may have heard claims about the largest structure in the universe. Over the years, astronomers have announced the discovery of various enormous structures, walls, and filaments spanning billions of light years. Some of these claims have been controversial, not because the observations are wrong, but because the definition of a structure is not always clear. When does a collection of galaxies stop being a random clustering and become a structure? How do you define the boundary of a filament? If two filaments happen to lie near each other, are they one structure or two? These are not just philosophical questions. They are statistical questions that require careful analysis. Different methods of analysis can produce different answers. A technique that looks for elongated features might identify a filament that a technique looking for over-dense regions would miss. A wall defined by one statistical threshold might disappear when you change the threshold slightly. The Hercules Corona Borealis, Great Wall, sometimes cited as the largest known structure at roughly 10 billion light-years across, has been questioned by some researchers who argue that it may be a statistical artifact, a chance alignment of smaller structures rather than a single coherent feature. Others maintain that it is real. Similarly, the Giant Arc, a crescent-shaped arrangement of galaxies spanning about 3.3 billion light-years, reported in 2021, prompted debate about whether it represents a true structure or a pattern that emerges from the way surveys sample the sky. The debate continues, and it may not have a clean resolution because the answer depends partly on what you mean by a structure. The lesson here is not that large-scale structures do not exist. They clearly do. The cosmic web is real. Filaments and walls and voids are real. They have been confirmed by multiple independent surveys mapping the three-dimensional positions of millions of galaxies, but the precise boundaries, sizes, and even the identities of the very largest individual structures can depend on how you define and detect them. Claims about the single largest structure in the universe should be treated with appropriate caution. The universe does not come with labels. We impose labels on a continuous distribution of matter, and different labeling methods can give different results. What is not in doubt is the overall pattern. Every major galaxy survey conducted since the 1980s has confirmed it. When astronomers measure the three-dimensional positions of millions of galaxies and map where they sit in space, the same architecture appears every time. Galaxies are not spread uniformly. They are concentrated along elongated structures stretching across hundreds of millions of light years, converging at dense knots, and surrounding vast, nearly empty regions. This is the cosmic web. It is not a model or a hypothesis. It is an observed structure, confirmed independently by survey after survey, each one mapping a larger volume of the cosmos with greater precision than the last. It is the largest scale arrangement of matter in the observable universe. And understanding how it formed, what it is made of, and how matter flows through it is the final step in the story of cosmic structure. At the largest scales, matter in the universe is distributed in a vast web of filaments, sheets, and clusters, separated by enormous voids. Galaxy clusters sit at the nodes of this web, where multiple filaments converge. Groups and individual galaxies are strung along the filaments like beads on a string, and the voids, the great empty regions between the filaments, occupy most of the universe's volume. This cosmic web is where our story reaches its largest scale. It is the largest scale pattern in the observable universe, the grand outcome of over 13 billion years of gravitational growth, acting on the tiny density seeds left behind by the Big Bang. Everything we have discussed, from the first collapsing cloud of gas that formed a star and its planets, to the dark matter halos that scaffolded the first galaxies, to the groups and clusters and superclusters that galaxies assembled into, all of it is connected. All of it is part of a single continuous process. Gravity pulling matter together, building structure upon structure, creating complexity at every scale. And the cosmic web is where that process reaches its grandest expression. Understanding it means understanding how sheets, filaments, nodes, and voids fit together into the architecture of the observable universe, how matter flows through this architecture even now, and why the interplay between gravity and cosmic expansion determines the ultimate fate of every structure we have encountered tonight. We have now climbed from planets to stars, from star clusters to galaxies, from galaxy groups to galaxy clusters and superclusters. At every level, the same physics has been at work. Gravity pulling matter together, dark matter providing the scaffolding, smaller structures assembling into larger ones. But there is one more level to explore. The largest scale pattern the universe has ever produced. The cosmic web. When astronomers map the positions of galaxies across enormous volumes of space, plotting where hundreds of thousands or millions of galaxies sit in 3 dimensions, a pattern emerges. Galaxies are not scattered randomly. They are not spread evenly. They are organized into a vast interconnected network of filaments, sheets, and dense knots, separated by enormous, nearly empty regions called voids. This network, stretching across the entire observable universe, is the cosmic web. It is the grandest architecture that exists in nature. And understanding it means understanding the full story of how structure formed in our universe. Let's start with the threads. Filaments are the defining feature of the cosmic web. They are elongated structures, like vast cosmic rivers of matter, stretching across tens or even hundreds of millions of light years. Each filament is made of dark matter, gas, and galaxies, with the dark matter forming the invisible spine and the galaxies strung along it like beads on a thread. Filaments are not rigid tubes. They are not fixed structures bolted in place. They are dynamic flows, channels through which matter is still moving today, pulled by gravity toward the densest regions of the web. A typical filament might be a few million light years wide, but hundreds of millions of light years long. Inside a filament, you would find galaxy groups, and even some small galaxy clusters, along with individual galaxies and thin streams of gas connecting them. If you could see a filament from the outside, it would look something like an enormous glowing thread, thicker in some places where groups and clusters reside, thinner in others where the density drops, but always stretching onward towards the next node. The filaments we observe today were first revealed by large-scale galaxy surveys. Starting in the 1980s and accelerating through the 1990s and 2000s, astronomers began systematically measuring the distances to hundreds of thousands of galaxies, then millions. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, mapped the three-dimensional positions of over 1 million galaxies. When these positions were plotted in 3 dimensions, the filamentary structure became unmistakable. Galaxies were not scattered randomly. They traced out long, thin structures, connected at nodes, surrounding enormous empty regions. The cosmic web emerged from the data not as a theory, but as an observed fact. The gas within filaments is often warm, heated to temperatures of hundreds of thousands to a few million degrees, much cooler than the superheated plasma inside galaxy clusters, but much warmer than the cold gas inside galaxies. This warm gas is extremely difficult to detect. It is too hot to emit visible light and too cool to emit strong X-rays. It occupies a frustrating middle ground where most telescopes cannot see it clearly. Astronomers call it the warm-hot intergalactic medium, and for decades it was essentially invisible, a predicted but unconfirmed component of the cosmic web. Only in recent years have observations begun to reveal it, using ultraviolet absorption lines from distant quasars, whose light passes through filaments on its way to Earth, and through a subtle effect called the thermal Sunyaev-Zeldovich effect, where the gas in filaments slightly distorts the cosmic microwave background radiation passing through it. The detection of gas in filaments was a major confirmation of the cosmic web picture. Computer simulations had long predicted that roughly half of all the ordinary matter in the universe should be in this warm-hot state, spread thinly through the filaments of the cosmic web, invisible to most telescopes. For years, astronomers jokingly called it the missing baryon problem, because this gas was predicted to exist, but could not be found. Finding it confirmed that the simulations were on the right track, and that the cosmic web is not just a pattern of galaxies. It is a pattern of all matter, visible and invisible, ordinary and dark, connected across scales that dwarf anything the human mind was built to comprehend. Now, think about what happens where filaments meet. At the intersections where 2 or more filaments converge, matter piles up. The combined gravitational pull of the converging flows draws more and more material into the junction. These intersections are called nodes, and they are the densest regions of the cosmic web. Galaxy clusters sit at these nodes. The most massive clusters, the ones containing thousands of galaxies and filled with superheated gas, are located precisely where multiple filaments come together, feeding material into the cluster from every direction. A galaxy cluster is not just a random pile of galaxies. It is the dense knot at the intersection of the web's threads, the place where matter from multiple filaments has been funneled together by gravity over billions of years. The relationship between clusters and filaments is like the relationship between a river delta and the rivers that feed it. Material flows in from multiple directions, accumulating at the point of convergence. The largest galaxy clusters can have 4, 5, or even more filaments feeding into them simultaneously, each one delivering galaxies, gas, and dark matter into the cluster's gravitational embrace. Some of these infalling galaxies arrive as members of groups, entire galaxy groups falling into the cluster along a filament, adding their combined mass to the growing node. This is how the most massive clusters in the universe built themselves up over cosmic time. This is why galaxy clusters are where they are. They did not form in random locations. They formed at the nodes of the dark matter web, where the initial density was highest, and where converging filaments continued to feed them long after their initial formation. Even today, clusters are growing. Gas and galaxies are still flowing in along filaments, falling into the cluster's gravitational well, adding to its mass. The cosmic web is not a fossil. It is alive. Matter is still flowing through it right now. Sheets and walls are another feature of the cosmic web. While filaments are essentially one-dimensional structures, long and thin, sheets are two-dimensional. They are broad, flattened regions where matter has collapsed along one axis, but not yet fully along the other two. Think of a sheet of paper floating in space, enormous in length and width, but very thin. Galaxies within a sheet are distributed across a broad plane, and the sheet itself forms a boundary between adjacent voids. Several prominent walls have been identified in galaxy surveys. The Sloan Great Wall, stretching roughly 1.37 billion light-years, is one of the largest. It was discovered in 2003 when astronomers plotted the three-dimensional positions of galaxies from the Sloan Digital Sky Survey and noticed this vast sheet of galaxies stretching across the sky. The earlier CFA2 Great Wall, discovered in 1989, was one of the first such structures identified. It extends roughly 500 million light-years and was a landmark discovery that showed for the first time just how structured the universe is on the largest scales. These walls are not solid barriers. They are regions where the density of galaxies is higher than average, forming broad, thin layers that separate the voids on either side. Sheets form earlier in the process of gravitational collapse than filaments do, and this is connected to a beautiful piece of physics that explains why the cosmic web looks the way it does. In the 1970s, the Russian physicist Yakov Zeldovich described how matter collapses under gravity in an expanding universe. The key insight was that collapse does not happen symmetrically. A region of slightly higher density in the early universe was never a perfect sphere. It always had some shape to it. Slightly elongated in one direction, slightly flattened in another. When gravity begins to pull this region together, the collapse is fastest along its shortest axis, the direction in which the region is thinnest. The result is a flat pancake-like structure, a sheet. This is sometimes called the Zeldovich pancake, and it was one of the first theoretical predictions of what large-scale structure should look like. The mathematics behind this are elegant. In an expanding universe, gravity must first overcome the expansion before collapse can begin. It overcomes the expansion earliest along the axis where the region is most compressed. So the first collapse produces a flat slab. Gravity is in one dimension but not yet in the other two. The sheet continues to expand in the other two directions, thinning out but growing in extent. Once a sheet is formed, gravity continues to work. The sheet begins to collapse along its next shortest axis, pulling matter into elongated structures within the plane of the sheet. These become filaments. And finally, at the points where filaments converge, matter collapses along the third axis, forming dense, roughly spherical concentrations. These become the nodes where galaxy clusters reside. The sequence is sheet, then filament, then node. Broad flat structures form first, narrow elongated ones form next, dense compact ones form last. This progression from two-dimensional collapse to one-dimensional to zero-dimensional is what gives the cosmic web its characteristic appearance. A network of thin threads connecting dense knots draped across broad walls with enormous, empty regions between them. One of the most powerful confirmations of this picture comes from computer simulations. Over the past few decades, astronomers have built increasingly sophisticated simulations of the universe's evolution, starting from the initial conditions recorded in the cosmic microwave background and letting the laws of gravity and gas physics play out over billions of simulated years. The Millennium simulation, run in 2005, followed the evolution of more than 10 billion particles of dark matter inside a cubic volume, roughly 2 billion light-years on a side. The result was a simulated cosmic web that bore an uncanny resemblance to the real one observed in galaxy surveys. Filaments, walls, nodes, and voids all appeared naturally from the physics of gravitational collapse. No one had to tell the simulation to make a web. It made one on its own because that is what gravity does to matter with slight initial density variations in an expanding universe. Later simulations like Illustris and its successor added gas physics, star formation, and the effects of supermassive black holes. These produced simulated universes containing galaxies of realistic shapes and sizes, arranged in cosmic webs that match the observed distribution of real galaxies with remarkable fidelity. The agreement between simulations and observations gives us confidence that we understand the basic physics of how the cosmic web formed. Gravity, dark matter, and gas dynamics operating over 13 billion years on the tiny seeds of the primordial density fluctuations are sufficient to produce the universe we see. Those empty regions are the voids. Cosmic voids are vast underdense regions where very few galaxies exist. They are not completely empty. A few lonely galaxies wander through them, and thin strands of gas and dark matter thread through their interiors. But compared to the filaments and nodes, voids are profoundly barren. A typical void might span 100 to 300 million light-years across. Some are much larger. The Buta's void, one of the most famous, stretches roughly 330 million light-years across and contains remarkably few galaxies for its enormous volume. When it was first discovered in 1981, astronomers were startled by how empty it was. Subsequent observations found a handful of galaxies inside it, but far fewer than the surrounding regions. The Boots void remains one of the most visually striking examples of how empty the universe can be. If you could somehow be transported to the center of a large cosmic void and look out in every direction, the experience would be profoundly lonely. The nearest significant concentration of galaxies might be 100 million light years or more away. You would see very few galaxies in any direction, and even those would be faint and distant. The night sky from a planet inside a void would look much emptier than our own. The universe from that vantage point would seem darker, quieter, more desolate. And yet, even inside a void, the laws of physics are the same. Stars still burn, planets still orbit. If there is life on a world deep inside a cosmic void, that life would look up at a sky with far fewer galaxies and might conclude that the universe is much emptier than it actually is. Interestingly, the few galaxies that do live inside voids tend to be different from galaxies in denser environments. Void galaxies are typically bluer, more gas-rich, and still actively forming stars. They have not been subjected to the crowding, merging, and gas stripping that galaxies experience in groups and clusters. Without neighbors to interact with, void galaxies evolve more quietly. They are pristine examples of what galaxies look like when left to develop in isolation. Their existence reinforces a central theme of our story. Environment shapes structure at every scale, from the molecular clouds where stars are born to the filaments and voids of the cosmic web. Voids occupy a tremendous fraction of the universe's total volume. Estimates vary depending on exactly how you define a void, but roughly 60 to 80% of the volume of the observable universe is in voids. Most of space is empty. The filaments, walls, and nodes where galaxies concentrate are the exception, not the rule. The cosmic web is a sparse structure. It is like a three-dimensional sponge, with thin solid walls and threads surrounding enormous hollow cavities. The matter is in the walls and threads. The cavities are the voids. And the cavities are far larger than the walls. Voids are not just passive gaps between the filaments. They are active participants in the evolution of the cosmic web. As gravity pulls matter out of voids and into the surrounding walls and filaments, the voids grow larger and emptier over time. They are expanding. Not because new space is being created inside them, although cosmic expansion does contribute, but because matter is flowing out of them, drawn by the gravitational pull of the denser structures on their borders. A void is like a puddle drying in the sun, gradually losing its contents to the surrounding landscape. Except, this puddle is hundreds of millions of light years across, and the process has been going on for billions of years. Over cosmic time, voids have become increasingly empty, while the filaments and nodes around them have become increasingly dense. The rich get richer, the empty get emptier. This is the fundamental asymmetry that drives the evolution of the cosmic web. This is the fundamental dynamic of the cosmic web. Matter flows from low-density regions to high-density regions. It drains out of voids, flows across sheets, funnels into filaments, and piles up at nodes. The web is a flow pattern, a gravitational drainage network spanning the entire observable universe, and it has been operating since the universe was very young, shaped by the same tiny density fluctuations that we discussed earlier in the story of galaxy formation. Let's trace this full chain one more time, from the very beginning to the cosmic web we observe today, because the continuity of this process is the central point of everything we have explored tonight. In the first fraction of a second after the Big Bang, quantum fluctuations in the ultra-dense primordial plasma created tiny variations in the density of matter. Some regions were slightly denser than average, others slightly less dense. These differences were minuscule, roughly 1 part in 100,000, but they were real, and gravity amplified them. dark matter, which makes up about 85% of all matter, responded first. It began collapsing into the denser regions, forming small gravitational wells within the first few 100 million years. These wells merged with neighboring wells, creating larger and deeper ones. A hierarchy of dark matter halos took shape, small ones embedded within larger ones, a nested structure of gravitational potential spanning a range of scales. Gas, freed from the grip of radiation after recombination, fell into these dark matter wells, cooled through radiation, and condensed into dense clumps at the centers of the halos. Within those clumps, the gas became dense enough and hot enough to ignite nuclear fusion, and the first stars lit up the darkness for the first time. Around those first stars, within those earliest dark matter halos, the first tiny galaxies assembled. Those early galaxies merged as their dark matter halos combined, building progressively larger galaxies over billions of years. Within these galaxies, molecular clouds collapsed to form clusters of stars, multiple star systems, and planetary systems. Each galaxy became an ecosystem, a gravitational environment hosting a rich variety of smaller structures within it. Galaxies gathered into groups held by shared dark matter halos. Groups fell into deeper wells to form clusters, surrounded by oceans of superheated gas that outweighed the galaxies themselves. And on the larger scales, the pattern of initial density fluctuations evolved into sheets, filaments, and nodes, with matter flowing along these structures toward the densest concentrations, while the voids in between grew emptier and the accelerating expansion of space shaped the outermost boundaries of the web. This is one story, one continuous chain. From quantum fluctuations in the infant universe to the cosmic web spanning the observable cosmos today, every level of structure we have discussed, planetary systems, star clusters, galaxies, groups, clusters, superclusters, filaments, walls, nodes, and voids is a link in this chain, each one formed through gravitational collapse. Each one sits embedded within the next larger scale, and each one is connected to the others by the same underlying physics. And the story is not over. The cosmic web is still evolving. Gas is still flowing along filaments into clusters. Galaxies are still merging. Stars are still forming in molecular clouds deep inside spiral galaxies. Planetary systems are still coalescing from disks of dust around young stars. At this very moment, somewhere in the observable universe, a cloud of gas is collapsing to form a new star. Somewhere else, two galaxies are in the process of colliding, their stars mixing, their dark matter halos combining into a single larger structure. Somewhere, a stream of warm gas is falling along a filament toward a galaxy cluster, accelerating as it approaches the deep gravitational well, destined to be shocked and heated to millions of degrees when it joins the intracluster medium. The architecture of the universe is still being built, still growing, still evolving, but it is also being dismantled. The accelerating expansion of the universe is slowly pulling the web apart at the larger scales. Voids are expanding. The connections between distant superclusters are stretching. In the far future, the web will fade. The filaments that currently connect clusters will thin and break. Each bound structure, each galaxy cluster, will become isolated. The cosmic web that we observe today, this magnificent interconnected architecture spanning the observable universe, is a snapshot of a particular moment in cosmic history. It has not always looked like this, and it will not always look like this. We happen to live at a time when the web is richly structured, when filaments and nodes are still connected, when the universe's architecture is at something close to its peak complexity. Future observers, billions of years from now, will see a much simpler, much emptier cosmos. If we could somehow rewind the clock and watch the web evolve in fast forward, we would see it thicken and sharpen over the first several billion years, the filaments growing more defined, the nodes more massive, the voids more pronounced. The web reached something close to its current richness perhaps 5 to 8 billion years ago. Since then, dark energy has been slowly gaining the upper hand, and the web has begun thinning at the larger scales, its most distant connections stretching and fading into the expanding void. Now, step back one final time and consider what we have learned. The universe began almost perfectly smooth. The matter within it was spread nearly uniformly, with only the faintest whisper of variation from place to place. And from that near uniformity, gravity built everything. Every structure we can see, every planet circling its star, every star cluster glowing in a galaxy's spiral arm, every galaxy spinning within its dark matter halo, every galaxy cluster burning with X-ray gas at the node of a cosmic filament. All of it was assembled by gravity, working patiently across billions of years, amplifying tiny initial differences into the magnificent architecture of the present-day cosmos. This architecture is hierarchical. Small structures nest inside larger ones. Planets orbit within stellar systems. Stellar systems live within star clusters or drift through the general population of a galaxy. Galaxies are embedded in dark matter halos. Those halos sit within groups and clusters. Groups and clusters are threaded along filaments and walls, and filaments and walls surround the great voids, together forming the cosmic web. Each level of this hierarchy is real. Each level has its own physics, its own characteristic scales, its own lifetimes, but they are all connected, all part of the same story, all built by the same force. And there is something deeply remarkable about the fact that we can understand this. We are standing on a small rocky planet, orbiting an ordinary star, located in a spiral arm of one galaxy among roughly 2 trillion in the observable universe. From this one tiny vantage point, using telescopes and mathematics and careful reasoning, we have mapped the distribution of galaxies across billions of light years. We have detected the invisible dark matter that scaffolds the entire cosmic web. We have measured the tiny temperature fluctuations in the cosmic microwave background that record the density variations from which all structure grew. We have built computer simulations that start from those initial conditions and reproduce the cosmic web in stunning detail, matching what we observe in the real universe. We have figured out the story, and everything we have mapped, every filament, every void, every cluster sitting at every node, exists within the observable universe, a sphere roughly 93 billion light years across. That is not the whole universe. It is simply as far as light has traveled since the Big Bang, accounting for the expansion of space. Beyond that horizon, the cosmic web almost certainly continues. The same physics that shape the structures we can see would have shaped structures beyond our view as well. There may be filaments, voids and clusters stretching far past our observable limit, part of the same web, but forever beyond our reach. The architecture we have explored tonight, vast as it is, may be only a fraction of what exists. Think about what that means. The universe produced, on one small world, a species capable of looking back at the universe and understanding how it works. Atoms organized by gravity into stars, stars into galaxies, galaxies into a web spanning the cosmos, And somewhere along the way, those same atoms, rearranged into DNA and neurons, became capable of comprehending the web they are part of. That is not just remarkable, it is, as far as we know, one of the rarest and most extraordinary things the universe has ever done. The cosmic web does not care about us. It has no purpose, no intention, no awareness. It is simply the outcome of gravity acting on matter across cosmic time. But we can care about it. We can find it beautiful. We can be awed by its scale and its intricacy. We can recognize the same physical laws that govern the largest filament in the observable universe also govern the fall of a raindrop on Earth, the orbit of the moon around our planet, the fusion of hydrogen in the core of our sun. The universe operates on the same physics at every scale, and we are part of it. Not observers standing outside the system, but participants, made of the same matter, shaped by the same forces, embedded in the same web. Every atom in your body was once part of a molecular cloud. Before that, it was forged in the core of a star or in the cataclysm of a supernova. Before that, it was primordial hydrogen drifting through the early universe, falling into a dark matter halo, cooling, condensing, becoming part of the first generation of cosmic structures. You are not separate from the cosmic web. You are one of its products. The hierarchy of structures we have explored tonight, from planetary systems to the cosmic web itself, is your family tree. The universe is almost entirely empty. More than 99% of it is vacuum. The matter that does exist is spread thinly across billions of light years, organized by gravity into a delicate web of filaments and nodes, surrounded by vast, silent voids. And yet, from that thin web, on at least one small planet orbiting one ordinary star in one galaxy, complexity arose, life emerged, consciousness ignited. And tonight, that consciousness looked out at the architecture of the cosmos and understood, at least in part, how it all fits together. That is the story of every type of cosmic structure. From the smallest moon circling its planet to the grandest filament stretching across the observable universe, it is one story. Gravity pulling matter together, building complexity from simplicity, creating architecture from nearly nothing. And it is still being written. We began tonight with a paradox. The universe is almost entirely empty, and yet matter has organized itself into a connected hierarchy of structures spanning billions of light years. Now you understand why. Gravity, working patiently on tiny initial seeds for over 13 billion years, sculpted that architecture. Dark matter provided the scaffolding. Gas cooled and formed stars within it. Stars gathered into clusters. Clusters lived inside galaxies. Galaxies collected into groups and clusters of their own. And all of them arranged themselves along the filaments, sheets, and nodes of the cosmic web, with vast expanding voids separating the threads. This is the universe. Not a random scattering of objects, but a connected, evolving, hierarchical architecture built from the bottom up by the simplest and most universal of forces. Thank you for joining me on this journey through the structures of the universe. If you found this exploration meaningful, a like or subscribe would mean a great deal. It helps me keep making these deep explorations of the cosmos. And the next time you look up at the night sky, remember what you have learned tonight. Those points of light are not just stars. They are parts of clusters, embedded in a galaxy, threaded along a filament of the cosmic web, connected by dark matter and gravity to structures billions of light years away. The universe has architecture, and you, standing on this small world, looking up, are part of it. The hierarchy of cosmic structures is not just an abstract catalogue of astronomical objects. It is the story of how the universe grew up, how formless matter became organized, how simplicity became complexity, how the same force, gravity, built everything from a rocky planet to a web of galaxies spanning the observable cosmos. It is one of the most complete and beautiful stories science has ever told. Good night, and may you never see the sky the same way again.